Hello and welcome to our lesson on applications of quadratic equations. We're going to look at some different word problems in this topic where we apply the different solving processes that we've talked about so far in this module, the processes for solving quadratics. So the application is just a way for us to use those processes or apply them in a new situation. Okay. Now word problems I know can be a challenge. Fortunately, the things that we're going to look at here, some of them we've seen before. But in general, they're difficult because there isn't one way to solve every particular problem. But there is a strategy, an approach that you should be taking. So you want to make sure that you read the problem first, and maybe a second time, maybe even read it a third time so that you understand what it's asking for. You can mark the text along the way. So if there are important things that you wanted to underline or highlight or list out, but when you read the problem and understand what it's giving you and what it's asking for, that piece that it's asking for is going to help you define the variable. So you want to make sure that you define the variable. That way, once you've solved, you know exactly what it is that you've solved for. If it's helpful to organize the information, again, into a list or into a chart, or to draw a picture in some way, organize the situation. So those are all sort of general strategies. The hard part here is to actually write your equation to model the situation, and in this case we're going to be writing quadratic equations. The good news is once we have our equation, we have a whole bunch of different ways in which we can solve. So we're going to use what's most appropriate or maybe the best method for you. If you don't choose the method that I choose, there are going to be multiple options for several of these problems. So we're going to solve using the method that we see fit. Well, it'll be me, whatever I see fit in this case. Sometimes we won't have an option, but sometimes we'll have several, okay? Now, when you're working on this on your own, remember, you can try to factor, you can try to use the square root method, you can attempt completing the square, or the quadratic formula. So quadratic formula is going to work every time. The other three, it will sort of depend on the situation, but those are your options. And I even put the quadratic formula on your note sheet here, so that you have that to reference if that's not already committed to memory. Okay. The last piece is once we solve, since we're looking at a contextual situation here, we want to make sure that our answer makes sense and that we answer the question with an answer that makes sense. So we're going to answer the question with an answer that makes sense. Okay. All right, first example, not too bad, and you might actually be able to figure this out without writing a quadratic equation, but the practice is good. So it says the width of a rectangle is 4 feet less than the length, and we're trying to find the dimensions of the rectangle if the area is 96 feet squared. So when it says to find the dimensions, that means we're looking for the length and the width. That means we have two unknowns, but we don't want to use two variables. I don't want two variables in one equation to solve, okay? So we have to determine which of these dimensions is actually the unknown. Which of the dimensions do we know nothing about? Well, it says that the width of the rectangle is 4 feet less than the length. So we know something about the width, we know it's 4 less than the length, but we know nothing about the length. So the length is going to be the variable here, and I'm going to call it L, just so that when I've solved, I know exactly what I've solved for, and that would be the length, okay? Now, if the width is 4 feet less than that length, then for the width, we can put the length minus 4. 4 feet less means subtract 4. So in our rectangle, just so I can draw this out for you here, we have a length of 4, a length of L, and then a width that is 4 less, so L minus 4 is going to go here. So we have our information all organized. It also tells us that the area is 96 feet squared. So now we got to take this information and make an equation out of it. And that's where that area is going to come in. The area for a rectangle is length times width. So in this case, our area is 96, and our length and our width are L and L minus 4. So if we distribute here, L squared minus 4L, we're going to try to factor this, so I'm going to subtract the 96 over. So L squared minus 4L minus 96. Is it factorable? Are there factors of negative 96? that make negative 4. Indeed, there are. You can use a negative 12 and a positive 8. And so we know this is going to factor into an L minus 12 and an L plus 8, which technically gives us two answers, L equals 12 and L equals negative 8. And if we had no context, we could just box those both in as our solutions. But here, only one of those is going to make sense for a couple of reasons. We cannot have two lengths for one rectangle, and also the length of a rectangle can't be a negative, so we're going to eliminate this L equals negative 8 as a possibility, which means L has to equal 12. So we know that the length of this rectangle is 12, and the units were feet, so 12 feet, when the width was 4 less, and 12 minus the 4 would mean the width would have to be 8. So you have a length of 12, you have a width that's 4 less, which is 8, and if in fact you multiply the 12 and the 8, that would give you an area of 96 square feet. So that is going to be our solution for this first one. Why? Just terrible. Let me use my cheat tool here to box that in, because it just... Nope. Alright, last time, and I'm going to leave it alone. Okay, that's better. So our length is 12 and our width is 8. Okay. And actually, I know I'm probably killing you here with my OCD-ness, but I don't like this rectangle next to my... What am I doing? Next to my other rectangle. I'm going to attempt this once more. Nope. Shoot! Okay, I didn't want to take both. Oh, no, I'm going to leave it alone. I'm sorry. Okay, moving on. Alright, let's look at the second example. So sometimes we'll see these geometric examples like the first one. Sometimes we have like the next two where we're just literally going to be translating. We're going to translate some words into an equation. So on number 2 it says that 3 times the square of a number is 5 less than 16 times the number, and our job is to find the number. So finding the number, that's what we're trying to do here. What do you want to call the number? I'm going to call it n for number. If you want to use x for some other variable, totally fine. All we have to do is translate what we're given here. So first it says 3 times. 3 times means 3 is going to be multiplied by something. So I'm going to put 3 and then my parentheses because I'm going to multiply that 3 by something. Now what am I multiplying it by? Well, it says 3 times the square of a number. So we called the number n. The square of the number would be n squared. And then it says is our equal sign. And then it says, oops, I can't see it because I made my green circle a little too big. Is our equal sign. It says 5 less than. 5 less than means subtract 5 from something. That's why I left a little space there. And then lastly it says 16 times the number. So 16 times my number is going to be 16n. And there it is. We have... Hello. Okay, we have 3 times the square of the number is 5 less than 16 times the number. That is our quadratic equation that now if we solve, we can figure out the number. So I'm going to get everything on one side and equal to 0, which means I'm going to subtract over the 16n and add over the 5, and then I'm going to hope this factors. 3 times 5 is going to make 15, and factors of 15 that make negative 16 are there. So this thing factors. This is good. Negative 15, negative 1 will work. And if I divide these both by 3 and then reduce, I see this is going to factor into an n minus 5 and a 3n minus 1, which means n is going to equal 5 and n is going to equal 1/3. Now in the last one, we got rid of one of the solutions. Here we're just looking for a number, and 5 is a number, so is 1/3, which means both of these are going to be acceptable solutions. So we're going to say the number could be 5 or it could be 1/3. Both of those are possibilities for our number. Now if it had some... Look at that, first try. If it had said find an integer that, satisfies the situation, then maybe we keep the 5 instead of the 1/3. But it's just asking for a number, and again, both of those are numbers. Alright, I've got one here for you to try. It's another translate problem, so if you feel comfortable, then give it a shot. If not, it says 9 more than the square of a number is 58, and we're trying to find the number. Again, I'm going to call the number n. If you want to use some other, shape tool's done. If you want to use some other variable, totally fine, but I'm going to call my number n. So first, it says 9 more than means we're going to add 9 to something. And whether we add it first or add it second, it doesn't matter. The commutative property of addition says we can change the order we add and still get the same answer. Not true for subtraction, so we have to make sure 5 less than means we subtract from. But addition, we can take first or second. Subtraction, if it's less than, has to happen after. Okay, sorry, just to clarify. So 9 more than means 9 plus, and then it says the square of the number. We're adding to the square of the number. So again, that's going to be n squared. And then is our equal sign. And then 58, don't have to translate there. 58 is 58, okay? So here's our equation. Our equation says n squared plus 9 is equal to 58. And we don't have to try to factor this one. We can solve using our square root method because we only have one term with the variable. So I'm going to subtract 9 from both sides, and that's going to leave me n squared equal to 49. And then to get rid of the square, I can take the square root. So n is going to equal, don't forget, oops, I swear I changed back. Good grief. N is going to equal, don't forget, your plus or minus in front of the square root of 49, which is 7. So without context, again, we could just box those in, but here we're looking for numbers. Both positive and negative 7 are numbers, so we're going to say the number could be 7 or negative 7. The number could be 7 or negative 7. Both viable options. All right, moving right along. So in the next couple of examples, hopefully you're going to see some things that look familiar. We looked at these types of problems in our rational units where we're dealing with fractions of polynomials. So for example, on number 3, it says that Abby rode 10 kilometers upstream and 10 kilometers back downstream in a total of 3 hours, and the speed of the current was 5 kilometers per hour. What was Abby's rowing speed? So if you recall, this is a distance, rate, time problem. So we're going to make a little table to organize the distance, rate, and time for Abby's 2 trips, for the one trip back upstream and the one trip back downstream. One trip up, one trip back down. Okay, so she rode 10 kilometers up, she rode 10 kilometers back down. So the distance for both trips was 10. And it says that happened in a total of 3 hours. So we know something about the time, but I don't know how much of the 3 hours is for the trip up or how much of the 3 hours for the trip down, so I'm not going to plop that into my table. We do know the speed of the current was 5 kilometers per hour. And remember, current either slows you down if you're going upstream against it or speeds you up if you're going downstream with it. So you're either going to add it or subtract it from the speed of, in this case, Abby, who is rowing. And so we're looking for Abby's rowing speed. Let's call that x. So her speed, her rate going up, we do not know, but we know whatever it is, she's going to be 5 miles or kilometers per hour slower because of the current. And her speed going downstream, whatever it is, she's going to be 5 kilometers per hour faster because of the current. Okay? So if we remember here, there were 3 versions of our formula. We could say distance equals rate times time, or that time equals distance divided by rate, or that rate equals distance divided by time. And the way we know which formula to use is by looking at what's missing in our table. Since the time column is empty, we're going to use the t equals version of our formula. So t equals distance divided by rate. T equals distance divided by rate. So I'm going to take my distance of 10 and divide it by my rate, which was x minus 5. And again here, distance of 10 gets divided by the rate, which was x plus 5. Now it says that the trip up and the trip back down took a total of 3 hours. So the time for the trip up plus the time for the trip back had to altogether accumulate to 3 hours. And that's where we get our equation. So we're going to have start over here just in case I need all the space. 10, let me change colors. So we have 10 over x minus 5, that's the time up, plus we have 10 over x plus 5, that's the time to go down. Altogether, that time took 3 hours. All right, so this is why we saw this in our rational unit, because this is not a quadratic equation yet. However, when we get rid of our fractions, it will become a quadratic equation. So remember, to clear out the fractions, we want to multiply to make common denominators. Once our denominators are the same, we can ignore them. They will no longer affect our problem. So the common denominator here is going to include one of each of these binomials. So I'm going to have to multiply my first fraction by an x plus 5 in the numerator and denominator. The second one by an x minus 5. I swear I gave myself space there. X minus 5 here and here. And then this third one's going to have to be multiplied by both binomials. And now just to confirm, all of my denominators now look the same. My denominators all have both binomials. So now that all of those denominators match, they no longer affect our problem. So now we can solve using just our numerators. So in the first numerator, we have 10x plus 50. 10x plus 50 plus, in the second numerator, 10x minus 50 equal to, in the third one, it doesn't matter the order you multiply. I would probably multiply the binomials first. I already know the x plus 5 and x minus 5. If I multiply that out, the middle terms are going to cancel and leave me a difference of squares, right? They're going to leave me x squared minus 25. So if I multiply these binomials, I get x squared minus 25, and then I still have to distribute the 3. So that's going to give me a 3x squared, and then 3 times negative 25 is going to make a negative 75. Okay, so now we have our quadratic equation, but we definitely got to do some cleaning up here, some simplifying. So we've got 20x on this side, and then 50 and negative 50 are going to cancel, and we still have 3x squared minus 75 on the other side. And then I'm going to get everything in order and equal to 0. So I'm going to subtract the 20x over and put it right in the middle so that it's all equal to 0. And is it going to factor? So let's see, 3 times negative 75. 3 times negative 75 is a negative 225. We need some factors that are going to make 20. Let me just, negative 225. Let's see, we used 3 and 75. That's not going to be a difference of 20. 5's going to go in. 5 goes in 45 times. That's not going to do it. 25's going to go in 6 times. 15 times 15. Yeah, I don't think. Let's see, 9's going to go in. 9 goes in 225 times. No, that's not right. What am I doing here? 225 divided by 9. Oh yeah, so what was it? The heck? Guys, I'm losing my brain. Okay, 25 goes in 9 times. I don't think this is going to factor, which is just lovely. And I could spend all day trying to factor it, but since I don't think it factors, or at least I cannot find the factors, I need to look for another way to solve. I cannot use the square root method because the two terms have variables there. That's no good. If I wanted to complete the square, I would have to deal with that coefficient of 3, so I'm not going to deal with that option either. So that means in this particular problem, I'm going to go with my last resort. I'm going to use the quadratic formula to solve. So for our quadratic formula, we're going to be plugging in, make sure I got enough space here, a equals 3. We're going to be plugging in negative 20 for b, and then c is going to equal a negative 75. So, need space. X is going to equal negative b plus or minus the square root of b squared minus 4. No space. Just probably happening to you too, right? Luckily, I have these little tools that let me move stuff around. Okay, negative b plus or minus the square root of b squared minus 4 times a times c. And this is all going to be divided by 2 times a. So we're looking at 20 plus or minus the square root of something. Let's figure out what that is. So we have a negative 20 squared minus 4 times a, which was 3, and c, which is a negative 75, and that gives us 1300 under the radical. And on the bottom of the fraction, the 2 times the 3 gets us 6. So if this problem had no context, I know you're having fun with this one already, right? If this problem had no context, I would say break down the radical and then try to reduce the fraction and box in your answers, whatever. But because this problem does have context, I wouldn't do that here. If we're looking for the speed in which Abby is rowing, I'm not going to give an answer that's like 20 plus radical 1300 over 6. I'm not going to give an answer with the radical in it because it doesn't make sense. It doesn't have a meaning to us. So because this is a word problem, I'm going to go straight to approximating these two answers. So this is telling us here that, that 20 plus radical 1300, just let me be, okay? Just let me be. All right, 20 plus radical 1300 over 6 is an answer, and it's also saying that 20 minus radical 1300 is an answer, right? So these are our two, what the these are our exact answers, the two exact answers. I want to approximate that, so I'm going to go to my calculator. Let's just try to stop talking here. 20 plus radical 1300, and then I want all of that to be divided by 6, and we end up with 9.34-ish. And then if I change this to a minus, we get negative 2.68-ish. Now, two answers, not going to be good for one Abby who is rowing in this stream. So I have to eliminate one of those. Obviously, I'm going to eliminate the negative. She's not going to have a negative speed. And so that means Abby is traveling at about 9.34 kilometers per hour. So she's going about 9.34 kilometers per hour. Super fun. I know that was like a ridiculous problem. Technically, some review is just when we solved this the first time in our rational unit, the only way we knew how to solve, the only way we had reviewed how to solve quadratics at that point was by factoring, and clearly that wasn't going to be an option for this particular problem. Okay, so fun stuff. Here's another one that should be a review in terms of the setup. So it says, working together, Tanner and Joel can grade their students' projects in 2 hours. Working alone, it would take Tanner 2 hours longer to grade the projects than it would take Joel. How long would it take Joel to grade the projects if he was working alone? So if you remember these, we can kind of set up in words first. Let's turn the draw tool off. We've got Tanner, and then if we added in Joel, then that would put them together. So we are given that working together, they can grade their students' projects in 2 hours. I'm going to put 2 hours over here for the together. Working alone, it takes Tanner 2 hours longer to grade the projects than it takes Joel. And Joel, we have no idea how long it takes him. So Joel is going to be our variable. We're going to put x there for Joel. Tanner takes 2 hours longer, so we're going to put x plus 2 here for Tanner. Now, if I left the equation like this, it's not going to give us a reasonable answer. It would give us 2x plus 2 equals 2, which would mean 2x equals 0, and that would mean x equals 0. No, it's not going to take Joel 0 hours to grade the projects. I know he's faster than Tanner, but he's not that fast, okay? Remember, what we have to do is convert these amounts to rates. So if they took 2 hours together, then they did 1/2 of the job per hour. if Joel takes X amount of hours alone, he does 1x of the job per hour, and then it's going to be 1 over x plus 2 of the job per hour for Tanner. So we want the reciprocal of the rate or the reciprocal of the amount to convert to a rate. And now we have our equation. So now we're going to solve by getting a common denominator, which in this case is going to have a 2 and an x plus 2. So least common denominator is a 2, an x, and an x plus 2, all of those factors. So this first fraction we're going to multiply by a 2 and an x. And then the second one, we're going to be multiplying by a 2 and an x plus 2. And then the last one is going to need an x and an x plus 2. And now just to confirm, 2x x plus 2, 2x x plus 2, 2x x plus 2. All of my denominators match, which means they will no longer affect my problem, and so I can continue to solve using just the numerators. So from this numerator, 2x times 1 gives me a 2x. And then here, 1 times 2 is still going to be 2, and then 2 times the x is going to be 2x, and then 2 times the 2 is going to give me a positive 4. Bring down the equal. Here, 1 times x is going to be x, times x is going to get me x squared, and then x times 2 is going to get me a 2x. So now I have my quadratic equation instead of my rational equation. And again, that's why we saw that originally in our rational unit. So this is 4x plus 4 on this side, equal to x squared plus 2x on this side. And let's see, if I get my like terms together and get everything on one side and equal to 0, we're going to be left with 0 equal to x squared minus 2x minus 4. Now this one, I can tell already, is not going to factor, and so I'm going to run through my options, okay, for solving. It's not going to factor. Can't use the square root method because I've got two terms with variables there. So I've got two options. I can complete the square, and this would be a nice one for completing the square because a is already 1 and the middle number there is even, so that's going to work out. If you don't like completing the square, then quadratic formula is absolutely an option too. But just so we've got a good variety in the notes, I'm going to go ahead and complete the square. So I'm going to move the constant back over. Let me take this over here. I'm going to move the constant back over, so I'm looking at x squared minus 2x, and then the 4 to the other side, so a negative 4 on the one side becomes a positive 4 back on the other side. And I want to figure out what I have to add to each side to complete the square here. So I'm taking half of b, I need another color. I'm going to take half of b, which is negative 2. So half of negative 2 is negative 1, and then I'm going to square that, which means positive 1 is my magic number. I'm going to add that to both sides. And so this side factors of 1 that make negative 2 are negative 1, negative 1. So this becomes x minus 1 squared. On the other side, 4 and 1 makes 5. And now I can square root both sides to solve. So square root. That means x minus 1 equals plus or minus a radical 5. And now I'm going to add the 1 over. And x is going to equal 1 plus or minus a radical 5. Now, no context, we would just box that in, but remember this is contextual here. We want to make sure we have an answer that makes sense to our problem. So this is saying that 1 plus radical 5 is an answer, and it's also saying that 1 minus radical 5 is an answer. So let's approximate these. Let's see, 1 plus radical 5, which is about 3.24, and then a minus is going to be about negative 1.24. And obviously, we can't have a negative amount of hours for, what was this, Joel grading papers, which means he's going to take about 3.24 hours. So we're going to say he's going to take about 3.24 hours. And I'm going to go ahead and leave it as a decimal. If you have something like this on your practice, it's the only way I'm going to be able to ask for it in Canvas. So 3.24 hours. If you wanted hours and minutes, let's see, 0.24 of an hour or 60 minutes would be 14.4. So it would be about 3 hours and 14 and a half minutes. Okay, something like that. All right, those are the two fun ones. Last one I don't think will be so bad. But obviously that is my skewed math teacher opinion. However, we haven't done one like this, so if you feel like you can handle it, something new I'm going to throw at you, then give it a shot. If not, let's attack this together here. So in this last one, it says the distance d of a falling object after t seconds is given by, we have a function here, d equals 4.9 t squared plus 30t. If a coin is tossed from an altitude of 75 meters, how long will it take to hit the ground? So they're giving us this function. They tell us that d equals 4.9 t squared plus 30t. And then it says the coin is tossed from an altitude of 75 meters. That's a distance of 75. And then it says how long does it take to hit the ground? So that means how long is it going to take for it to get all 75 meters from where it's dropped all the way to the ground. So we're trying to travel that entire distance of 75 meters. So it's saying how long is it going to take for that to happen? Then I don't know. T is our question, okay? So this one's a little easier, in my opinion, than the others because we don't have to write an equation. We actually have one given to us. So technically it's a function because we've got the two variables in there, and they're giving us the value for one of the variables and asking us to find the other value. So how do we do that? Well, we plug in the one we know and find the one that's missing. So we're going to plug in the 75 for D. So we're left with 75 equals 4.9 t squared plus 30t. And now we have an equation that we can try to solve for t. So I'm going to move the 75 over. So we have 4.9 t squared plus 30t and then minus 75 equal to 0. I'm not even going to try to factor that, not going to try to complete the square. Using the square root method, not an option, so I'm going to go straight to the quadratic formula. So in our formula, let's go back to blue. A is going to equal 4.9, B is going to equal 30, and C is going to equal a negative 75. So t in this case, instead of x, is going to equal a negative b plus or minus square root of b squared minus 4 times a times c, and that's all going to be divided by 2 times a. So t is going to equal a negative 30 plus or minus the square root of, let's figure out what we have under the radical there. That's 30 squared minus 4 times 4.9 times negative 75. And we get 2,370 over 2 times 4.9, which is going to be 9.8. Come on. 4.9 times 2, so 9.8. Now again, if we had no context here, I would say simplify the radical, try to reduce, but since this is going to be an answer to a contextual problem here, I'm not going to give an answer that has a radical in it, so I'm going to go straight to approximating. So we've got t equal to negative 30 plus radical 2,370 over 9.8, and we also have, oh gosh, let me put this up here, space. Can I fit it? Maybe? Come on. Okay, so let's just do a little... Okay, so we've got the positive, and then we also have the negative radical 2,370 over 9.8. So we have to approximate both of these. So let's get rid of all that. We've got negative 30 plus square root of 2,370, and we want all of that to be divided by 9.8, and so we get approximately 1.91. 1.91, and then if we change that to a negative, we already know we're going to get a negative 8.03-ish there, and since this is a time that it takes for this object to fall from the 75 meters up to the ground, we know that's not going to be a negative time, so we're going to say it's going to take about 1.91, and this was seconds. So this is going to take about 1.91 seconds, or about 2 seconds. If you wanted to round it, that would totally be okay. But since we have some of the decimal, I'm gonna keep it. Terrible. This cheat tool is supposed to help me make the rectangle. There we go. That's better. All right, so there it is. Obviously, I think the ones in the back were a little harder than the ones that were on the front there. You've got a few practice problems to try out. I know the word problems are challenging. Work through them the first time. There is some pretty good feedback in there, so if you don't get the right answers the first time around, check the feedback. I try to give you some help on how to set up the problems. The solving piece really shouldn't be that bad. It might be a lot of work, but that's work that's a little more manageable sometimes than the setup. Okay, so give them a shot, but as always, if you need some extra help, then just reach out. All right, guys, take